Okay, so for those of you that might be interested in sort of where the formula for the confidence interval comes from, this video is for you. So remember we talked about the distribution of the sample mean x bar, right? This came from our central limit theorem. For any sort of the normal distribution, the mean of the x bars is going to be right at the population mean mu. Okay, so that's here, right? And the standard deviation of x bar was this sigma over the square root of n. Okay. Now let's pick some sort of value here. So I'm going to go with 95% as sort of our confidence level, right? So so if I were to go out, just because it's a common one. So if I were to go out 1 standard deviation, 2 standard deviations, this value here, that's going to be my mean plus 2 standard deviations. I'm going to call it 1.96 because that's more accurate, but we're going to go at 1.9 standard deviations to the right. Okay. And if I go 1.96 standard deviations to the left, so mu minus 1.96 sigma over the square root of n. Okay, this area in here, I could work that out. Okay, so this area in the middle, I could work that area out. It's 95%. So if I wanted to do that, right, this would have a z-score of minus 1.96, and this one would have a z-score of positive 1.96, right? So that would be p norm is the R code, and if you put in 1.96, that will tell you the area to the left, which in this case is 0.975, right? So that'll give you the area to the left, and then p norm of minus 1.96. If you plug that into R, it'll give you 0.25. And if you subtract those two, that'll give you the area in the middle. So it's 95%. Okay, I picked this one on purpose because it's sort of a common one. Okay, so all of that to say, you know, considering all the possible different intervals where we get these different x bars, blah, 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 out of all the x bars, the probability, okay, of x bar being between those two values, so mu minus 1.96 sigma over the square root of n, and mu plus 1.96 sigma over the square root of n, the probability that it's between those two values is 95%, approximately. Okay, and again, I just picked those, the 1.96 and the 95% because it's trivial. I'm just trying to pick an example of something that's common so you can sort of see how these intervals are constructed. So then from there, we can do a little bit of algebra, right? We've got sort of, I don't know, you can picture like 3 sides of an equation here. And we're going to do a little bit of algebra here to try to rearrange this until mu is in the middle instead of the x bar. Okay, so the first thing that I'm going to do is I'm going to subtract x bar from everything. So I'll have mu minus 1.96 sigma over the square root of n minus x bar. Just leaves me with 0 in the middle. Oops, I added an equal sign. Not that it really matters. And then we've got mu plus 1.96 sigma over the square root of n minus x bar. Okay, so that was the first thing. All I did was sort of subtract x bar from each side of the equation. Okay, then from there I'm going to subtract mu. So I'll have 1 negative 1.96 sigma over the square root of n minus x bar minus mu, and then positive 1.96 sigma over the square root of n minus x bar. Good. So probability that minus mu is in between those two values. And then from there, I'm going to sort of, you can think of dividing everything by minus 1. When you divide everything by minus 1, your signs flip, right? So just an algebra rule, right? So if I divide everything by minus 1, I've got minus 1.96 sigma over the square root of n minus x bar over minus 1 is going to be, flip the signs, mu, flip the signs. So this will be minus 1.96 sigma over the square root of n minus x bar over minus 1. I personally hate it when the signs are flipped like that. So I'm going to reverse the order of the things, right? So if this piece here is the smallest thing, I'm going to write that on the left-hand side. So I'm going to say, okay, 1.96 sigma over the square root of n minus x bar over minus 1 is less than mu, is less than, and then I'm going to put the biggest thing over here. So that's minus 1.96 sigma over the square root of n minus x bar over minus 1. All of that has a 95% chance of being in there, and then we can simplify this a little bit. So if I divide by minus 1, I'm going to end up with x bar is going to be positive now, and minus 1.96 sigma over the square root of n. That piece is going to be minus, and I just, again, flip the order. And here we'd have x bar is now going to be positive, and so is the 1.96 sigma over the square root of n. Okay, so all of that algebra to just get this piece here, right? So now mu, the population mean mu, is on the inside. So this is saying that, you know, in repeated sampling, if we're considering lots and lots of different x bars, okay, the proportion or the probability that those intervals, this interval between minus, from x bar minus 1.96 sigma over the square root of n to, let me write out the interval rather than just saying it, right? So this interval, x bar minus 1.96 sigma over the square root of n, x bar plus 1.96 sigma over the square root of n, that interval is going to contain mu about 95% of the time, considering you know, repeated sampling, if there's lots and lots of different x bars. So maybe I should add a statement in there and say something like with repeated sampling. This interval is going to contain mu about 95% of the time. So again, that's sort of where our formula is coming from. Again, for this particular example, I picked a particular value, this 1.96 for our critical value, because it worked out nicely to be this 95%. But obviously in, you know, we've changed in the formula, this becomes z alpha over 2, which is a little bit more general. So for any area you want in the middle, any value of confidence, you could work out what the critical value should be.